The first speaker of this part of the session is Dr. Omid Chatrabgoun. He is a lecturer at Coventry University, and he's going to talk about the state value function approximation in reinforcement learning from on-policy data. Dr. Chatrabgoun, please go ahead.
Thank you so much. Thanks for your good introduction. You share some useful information. I am from Iran, but to be honest, I didn't know some of that. Thank you again for sharing some useful information. So my presentation is a state value function, and my time is 20 minutes, yeah?
You can go up to 25 minutes, that's fine.
Yeah, good, thank you. So my presentation is about reinforcement learning and how to approximate the state value function in a reinforcement learning, because we have a complicated situation. We can't exactly find a state value function, and we have to approximate because the environment outside is complicated, and sometimes your agent goes through the environment which is unfamiliar, and agent haven't been and haven't seen this environment before. So for this reason, we need to approximate a state value function. So what is the outline of my presentation? First, brief introduction about state value function and why we need to approximate. Second step, I will review some approximation function, for example, Fourier, polynomial, wavelet, neural network, and one of the nice way. And then I will share with you one of the nice way we approximated that one in one of the research paper I have done with my colleague in Iran. I wanted to invite him and have a presentation together, but unfortunately, because of the internet connection is Iran, I couldn't invite him. We try our best, but he couldn't join our presentation. And we have done application about robotic and how, for example, we can approximate a value function for a robot. And at the end, I will share some results, takeaway, conclusion, and open question. Please, if you have any question, you can interrupt me and ask your question. So what is a reinforcement learning? I'm sure you have a background about reinforcement learning, but let me share with you a simple instruction about reinforcement learning. In reinforcement learning, we have an agent. An agent make a decision based on a environment and put himself in a different state. And this is and based on being in a different state, collect some reward. If it is a positive action, the reward will be a positive, and if it is a negative action, the reward will be a negative reward. But for make action in different action, we need a policy, and this policy is very important for us going through the policy. But sometimes, as I said, the environment is complicated, and we need an online policy or on policy reinforcement learning. So why we need to approximate the value function? Value function, a simple definition of a value function is that value function means when we are in a state S and we want to, for example, go through next state, what is our expected return or expected reward? And knowing about that is very important, and main objective and final objective of many reinforcement problem is to find this state value function based on a policy. So and on policy is very important because we need to have a policy to make a decision and guide the agent in different and complicated environment. I can share with you a simple example. For example, we have a robot, and this robot, if we consider a grid, and the size of the grid, for example, is 100 by 100, we can, for example, have a policy and approximate and estimate the state value function. But when the grid is very complicated, for example, 1 million by 1 million, it is difficult to find the value function and optimize the value function, and we have to approximate it. But for approximation, we can consider some basis function and consider value function as a linear combination of some basis function. This basis function can be Fourier transformation, polynomial approximation, wavelet, and neural network. Each one has a pros and cons. For example, the locality for Fourier transform is a low, and we can't, for example, find a more locality in a Fourier transform. Polynomial, we have a worse situation, and it's a very low. Some of this technique we have a convergence, but some of them, like a neural network, we can't guarantee the convergence. After approximation, this means approximation by some basis function. After approximation, we should find the coefficient of this approximation. For example, when we say, oh, this value function is a linear combination of this Fourier basis, we have some coefficient and we need to find this coefficient. And as usual, we have a free technique for find the approximation of value function. MCMC, dynamic programming, and TD. In this presentation, I have used a TD method, which is a nice method when we want to find the approximation function. What is the limitation when we use, for example, this different basis function, Fourier, polynomial, wavelet, and neural network? As I said, one of them is the locality. We had a locality issue because the Fourier transformation is not enough flexible, and we can't, for example, adjust based on a locality, and it is essential for high dimensional space. As I said, for example, when we have a robot in 1 billion by 1 billion grid, and should be sometimes should be non-smooth value landscape. So we need a technique to estimate non-smooth value function, and also sometimes on policy data is expensive, and we need, for example, technique. This technique should be converged, and sometimes we need some technique to approximate a non-linear value function as a linear combination. And we decided to use a kernel-based approximation because, as you know, kernel-based approximation in a Hilbert space and reproducing Hilbert space can guarantee all of this technique for us. So what is a radial basis function and kernel approximation? In radial basis function, we have some state, and for this state, for local state, we consider a center. So this means, for example, when we are in state S and jump to another state, we have a center, and look at this one as a cluster. When we move this cluster and move out of this cluster, we can jump to another cluster and consider another center. So this, considering this center localize us. And this is one of the benefits of radial basis function and kernel approximation. And also we have some parameter here, which is a hyperparameter. It is like a variance in Gaussian distribution. And by playing with this parameter, we can, for example, consider more general or more localized approximation function and approximate value function based on the situation, based on the condition we are in. and this is very important. So we approximate value function based on a linear combination of some kernel. This kernel again can be a linear combination of different kernel. And based on a kernel property, it can be, for example, supported kernel or on compact kernel or uncompact kernel. Compact kernel means the domain of the kernel is a cloud, but uncompact means we have an infinite domain of for the kernel, like for example Gaussian kernel. And it is something like when we consider something like this, it is exactly equivalent to consider Gaussian process prior for a value function and for approximating of the value function. Just we consider, for example, the kernel K as a covariance of the Gaussian process. And if someone asks, what is the benefit of this one? We discuss the benefit, but for example, one of the very important one is locality. And here locality is very important. For example, if we work with a Mattern kernel, which is a compact support kernel, it is very important to give us a locality, because based on it, when we have a complicated space like a robot, we have a different situation, we have a different position, and for example, position A to position B is totally different, and so we need to localize this value function. So consider an example for a robotic. As you know, for a robot, we can consider a different degree of freedom. One of the simplest one is a 2 degree of freedom. 2 degree of freedom, for example, means we have a 1 degree in a shoulder and 1 degree of freedom in a elbow. This is one of the same, but we can, for example, consider more complicated robot with a more degree of freedom, but 2 degree of freedom is one of the easiest one. And we have a 2 angle, θ1 and θ2. θ1 is the angle from the shoulder, from the horizontal line, and the θ2 is the angle of the elbow. So the reward function is end of effector, end of the robot hand, minus target, and or priority here is the minimize this reward, but to be adopted with a reinforcement learning problem, we consider minus of this reward. So exactly like other reinforcement learning problem, this is maximization, and we want to maximize this reward. And it's very important to maximize this reward, because we can make sure the hands of the robot targeted reach the target point, and it is very important in there's something like this robot. So in this research paper we have done before, we consider different kernel approximation, and the learning algorithm we have applied exactly was a TD, a temporal difference for a learning, and we compared with a different technique, for example, Fourier basis with 35 feature, Zhao-Bichy wavelet, order of 4. We know, for example, for a wavelet function, we have a scale function, an approximation function, and one of them is a detail function and a scale function. Detail function provide more detail about the approximation, and a scale function scale your function. And also we consider neural network with 2 layer and 64 unit, and this is the result of the result of the comparison of different technique. As you can see, the RMSE for kernel RBF is a minimum 1, and also the convergence has been guaranteed here, and we have done a full KLSTD, and this is a RD kernel, a radial basis function kernel, and we get less RMSE here. So we can extend this one to other domain. For example, for navigation, what is the position, what is the velocity, what is the obstacle, and consider, because for example, something like a Google map and something like a self-drive car, the situation and the environment is very complicated, and we need to approximate the value function, and we can't work with a straightforward approximation function, and sometimes we need to and we have a non-linear value function, and we need to approximate with a combination of linear bases and make it as a linear combination of some bases. Game playing, again, when you play a game, the environment sometimes is complicated, because when you start playing a game, you know, for example, after some time, the stage 1, stage 2, and move to the higher state, and every time the game will be more complicated and complicated, and we know we need to again consider something like this. So what is the takeaway of this presentation? On-policy value function is challenging because of the data distribution shift, and we can't reuse off-policy transition. We should be online for on-policy. The classic basis like Fourier transform, wavelet approximation, sometimes the trade-off between global and local. For these two technique, locality and convergence have been guaranteed, but for the something like a neural network, you can't guarantee the convergence. And because of the some nice property like a locality, adaptivity, yeah, we have started work with a kernel method. We compared kernel method. We used a combination of different kernel method, and as you can see, we have seen a good result for robot example, and we can use this one in another example like navigation, game, and logistics. So what was the issue? The issue was computational complexity. When we replace the kernel bases with a Fourier basis or something like this, the order of computation is n cubic, and this is a high level of computation. And sometimes we need to approximate a kernel. For example, truncate kernel after some level, when we don't need a more detail about kernel, and it's very important to truncate kernels as we can, and because the degree of approximation and the degree of accuracy is very important for us. And another side, we want to have a trade-off between computational level. This is one of the challenges. We can fix these challenges with some approximation technique. And in one of the paper, we have used one of this approximation technique. Yeah, this is some references. We have written some of this paper with my colleague, Dr. Ismail Beiki. And as I said, we couldn't, unfortunately, because of the connection issue, I couldn't invite him to this meeting and have a presentation together. Yeah, thank you so much. Yeah, I think I finished in exactly 20 minutes. If you have any question, let me know.
Okay, thanks, Dr. Chatrabgoun, for the presentation. If anyone has a question, you can raise your hand. And any question from the audience? Okay, if not, I can go a few myself. So for the robotic problem, we have the forward problem and the backward problem. I think you were talking about the backward problem. You have a location that you want the arm to reach that position, right?
Yeah, exactly. Yeah.
When we do it with the polynomials, What I remember is that there are some configuration that are not good. We were trying to avoid them. For example, there is a configuration if the robot arm is in that position and then it wants to move the arm before the endpoint to be able to move, you have to change the other parts of the robot arm, and then it's a waste of energy because the endpoint is not moving as a result of those change. Which were corresponding to the singular points of the polynomial map. Is this reinforcement learning method able to avoid those paths or have a smooth path with all the moments being spent on a useful movement?
Yeah, to be honest, what we have tried in this research paper, we try to make the movement very, very simple and just try to, for example, robot pick some target point in a vertical line. Yeah, because if you change it, you need some rotation, and the angle of the robot should be, for example, more than 2 direction. But what we have done, just we, for example, try to define 2 angle, and based on only 2 angle, do the move forward. And if you need something like that you describe, you need a more than 2 angle, and it make a problem very complicated. Our objective or final objective was not to work with a different movement of robot. Just we wanted to show, because one of us is a mathematician and another one is a data scientist. Just we wanted to show that this kind of approximation, kernel approximation, can help to, for example, approximate a nonlinear value function in a best way.
Okay, thank you.